All right. Welcome everyone to the 55th episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Dr. Kevin Mongeon from the University of Ottawa, who's going to speak to us about or give a talk entitled From Pre-Game Priors to Real-Time Updates for In-Game Win Probabilities. Dr. Mongeon is an associate professor of sport management in the School of Human Kinetics in the Faculty of Health Sciences at the University of Ottawa. He received his PhD in economics from Washington State University in Pullman. I guess you think that's the first ranked college town in the USA in 2010. His research focuses on sports economics, sports analytics, and applied econometrics, and he's been published in leading economics, statistics, business, and sport management journals. His work has examined the production of winning, discrimination, and roster design in professional and amateur sport, and he has consulted for NHL and NFL clubs. Dr. Mongeon is the co-editor of the inaugural Springer book series in sports analytics. In terms of a talk abstract, in-game decision-making in professional sport increasingly relies on win probability estimates, yet many existing models are either opaque to decision makers or too computationally intensive for routine use. This study introduces an outcome-first modeling framework that produces transparent, straightforwardly computable, and probability-coherent in-game win probabilities in real time. Using professional basketball as a motivating context, we model the distribution of the score differential at each game minute conditional on each terminal outcome and estimate these outcome condition moment paths from 3 seasons. The resulting closed form mapping from any intermediate game state to a current win probability is then evaluated on a held out NBA season where we assess accuracy, calibration, and temporal coherence of the predictions. The empirical results show that the proposed approach, delivers well-calibrated, interpretable in-game win probabilities while remaining computationally lightweight. So, it sounds like a really timely problem in our field. So I'm going to hand it over to Dr. Mongeon to give us the details. Thank you for joining us. Oh, you're still on mute there.
Thanks.
There we go.
Share my screen here. That's I've never heard my abstract kind of read to me before. It's pretty dense.
Those are your words, not mine, but
Yeah. That's a mouthful.
yeah, I don't know.
If I
That's
could
pretty clear.
throw more information in that. Yeah. There we go. How's that looking?
I don't. Oh, there we go. Okay, so I clicked. Yeah, I have a separate tab on my Zoom if those of the rest of you are looking for it. So I can see you. I see your overlaid presenter on your screen. So that looks good.
Would you rather I
I
can change it? Are we good?
think we're good.
What's the normal
I mean, normally you just have the regular screen share, and then we have the speaker video in the corner there. But this is
oh,
new.
you mean not even know.
Let's try it this way.
Side by side? No. I guess I pressed a button and I shouldn't have.
Yeah, I'm not sure. So yeah, so do you see yourself? You've got yourself with your screen in your background.
I don't. I see the screen in the background though. Yeah, I see it. I'm gonna stop sharing here, then I'll share. Let's try again. No, it's gonna do the same thing.
Yeah, I'm not from. I've never had that kind
Yeah, messing things up, eh?
of overlaid like that. Zoom's getting fancier by the day.
I got screen sharing is paused right now.
Really? It should be.
How's that? You get nothing, eh?
No, here, I'm gonna just switch. One participant can share at a time. Uh, maybe I need to, let's see. Can you try sharing again? Oh, there we go. So it looks like you're sharing, but we can't actually see your presentation at this.
Hmm.
Do you just have a black screen
Yeah,
as well?
record.
Here we
All
go.
right. Yeah. Thanks, Dave. And Sports Analytics SFU and the Sports Analytics group. Um, you know, long time listener, first time presenter, appreciate it. And I guess before I start, this is this presentation paper project is joint work with my colleagues from Washington State University. So thanks to them for their kind of work on that. And then I guess another little bit of housekeeping and blatant self-promotion. Myself and Shirley Mills from Carleton are just starting up a sports analytics textbook series with the fine folks from Springer. So if anyone's interested in putting together a textbook or a chapter or being involved in that, feel free to reach out to myself or Shirley. And then thanks to my PhD students who are doing some pretty good and kind of innovative work in sort of sports analytics and economics. It's fun to work with them. So thanks to them. Now, so I guess just a bit of an outline on the paper. We're going to move from, I guess, sort of why the got into this project or building this model into the right through the how. So and hopefully along the way, um, I'm going to kind of build up and see if the um, conceptual framework motivates the empirical approach a little bit. Um, but so I guess, just to motivate the in-game win probability model, right? I think it's if you had to kind of define a little bit of a curriculum of sports analytics, it's kind of quickly becoming part of the mainstream, concept for a number of different reasons. I think there's an active body of literature that analyzes in-game winning, probabilities across a lot of different sports. They use a lot of different methods, and it's potentially some of it might be driven by the increasing accessibility to granular data and ability to more compute. Um, I think that the the models or the application have a lot of practical applications. They're from right from in-game sort of decision making or maybe not even in-game but by teams or leagues or at the television and be used for deriving metrics, let alone kind of betting and those type of things. And I think kind of how I ended up getting into it is developing sort of an in-game winning model as a means to testing for another kind of economic phenomenon. And I think that's kind of some of these models are used for that um, in a whole bunch of different contexts. So a little bit about the previous literature, right? So this paper is, we're going to use basketball as an application, and I think hopefully, the model can be generalized across a lot of different sports. But as we kind of look at the literature, see a few different things. Is first of all, there's they use a lot of different paradigms in order to come up with these win probability models, right? Right from Brownian motion to kind of Poisson models and Markov models to traditional regressions, right through to more kind of Bayesian models with kind of latent variables. And you kind of see the same thing across other sports, right? I'm I can kind of throw myself in that mix with a Markov model that analyzed. I think it had. Well, I know what it had exactly. It had every game second in it. So every and it was a Markov model based on game seconds that accounted for transitions with man advantage. And so you see these things in football and more data, right? So um, it's kind of broad in scope, and overall, I guess if you had to take a look back at the literature, I kind of would describe it as a little bit of fragmented, right? So people kind of, you know, they seem to start, coming up with win probabilities from a whole bunch of different places. Right from score probabilities to just starting off by estimating the likelihood of a win, to building up on top of win probability or gambling models, right? And and then as the data became more and more available and detailed, people started to control and account for very more and more different things and different factors, and became computationally more the models are more and more computationally intensive. I guess there's a scale of that, and and then and as they become computationally intensive, sometimes it's not quite as easy to decompose them or maybe use them um, in practice, let's say, to just update on a ongoing uh, or a live basis, if you will. So I guess I would just a little bit of terminology, right? Is if I could characterize maybe one way to characterize the existing literature, I would say they would take a data first approach by that. And by that I mean, at some point there people are using certain model or modeling paradigm to estimate the probability of a win, right? Conditional on a bunch of data just directly. And then, the size of the data or the variables in the data, right? That all might change, and the method might, um, the method varies by sport or whatever that is, right? Um, and that's similar regardless of kind of the dependent variable. So in this paper, right, I'm going to do a little bit of motivation, and we're going to use an outcome first model where we literally we invert it and we kind of estimate the probability of the data conditional on the outcome. And then we use Bayes' rule to invert it back and come up with a probability, right? So we don't actually use Bayesian regression in here, just Bayes' rule to back out the probability in the end. And I would suggest that sports and in doing so, I think we substantially simplify the estimation problem, right? And hopefully we can kind of see that through this, in this paper or presentation. And I would say sports is kind of a good environment maybe to implement this type of approach. Because it has these finite outcomes where we can divide the data by outcomes, wins and losses or wins, and we have a whole bunch of historical data that allow us to estimate the probability of the data. And then key, right, which can get overlooked here if we don't take time to do it, is to use Bayes' rule and get the probabilities, is we're going to have some prior probability of the outcome of a game. And in sports, the games are repeated, and there's information from a variety of different sources to come up with. I would suggest is you know an excellent prior that accounts for a large majority of the factors that a lot of the other models are attempting to control and account for. So that's kind of the environment where that we're in. And so just broadly, right, we just look at any kind of sport game that progresses from the beginning, from the end. We start at time zero and go to one as a fraction of the game. And for the analysis, we just include regulation time games, although games that go into overtime are still in the sample. They just model them. And then for basketball, you could think of the minutes going from from 1 to 48. So we actually have, um, game minute observations. And then the key sort of variable that we have in there is the score state, right? Which is the data, which I'll say is we've just represented in terms of the whole time, the home team, right? The score of the home team minus the score of the away team, and at time zero, right? All teams are starting at zero. And so what we have is we have a terminal outcome, so games end, and there's either a win or a loss, right? And then the last little bit is we have these, we have pregame probabilities, the probability of the home team at the beginning of the game before the game starts, and one minus is the probability of the away team, right? And so we can come up with that probability however we kind of choose to do it, and we kind of make some assumptions about the model, right? Um, that the mean score, right, increases, given our games that home team won, the average score differential increases with time. And games that home teams lost, the average score differential decreases with time, right? And so that's a nice kind of standard, economic, I don't know, assumption or outcome of it. And we'll kind of look at the data and see that. And so, so we just kind of have that as our framework, and then we just use that and update it, use Bayes rule to update it. And so we just classic Bayes rules, the probability of the home team winning, given the scores, that's really what we're looking to estimate. And we can flip that by, inverting and estimating, well, what's the probability of the score at any given time, given the home team won, right, weighted by the probability of the home team. And if we represent that in odds form, right, it kind of comes out nice, and we can uh, represent the relationship in an odds rather than a probability, and we think of what are the odds that the home team wins, right, on the left hand side, and we get the ratio of the odds of the home team winning before the game starts, right? The pregame odds, and we're left with the Bayes factor or the likelihood ratio, which is the size of that is. What's the probability of the home score at any given time conditional on the home team winning, and what's the probability of the score given the away team won, right? And so there's kind of two important points here. Is we need to be able to specify the prior. Without the prior, right? This is just a kind of a formula, but we could the prior, if we can come up with a prior about an accurate prior that represents the likelihood of the home team winning, right? I would suggest that it aggregates most of that pregame information, right? That the data first approaches attempt to encode through either their method, their covariates, their specification, right, or whatever that is, and there's a lot of different uh, you know factors in there, but it might be easiest to think of as just team strength right there. Um, and then the other key thing is we have to have historical data that is representative of the current data to be able to estimate these inverse conditionals, right? What's the probability that the home team of the score given a home team win and a home team loss? And in sports, we have this repetitive games, right? And lots of historical data that accurately represents that. So I think we kind of meet these kind of these conditions. Um, and then we just represent um, Bayes rule in odds form with an empirical specification where what we're really looking to do is estimate that inverse conditional, the probability of the score state, um, given a home team win or loss, and it's really that f at x, and we can do that a number of different ways, right? I'm going to pull out, we're going to kind of pull out the normal distribution in this presentation, but at some point we could just be using means, right? So we're going to use whatever density function we think is best to represent the sport, at the time. Um, and we're just going to substitute that in. And and then we introduce theta as this time variant parameter that we use with our density function, right? So that's the kind of uh, nuts and bolts of the empirical approach. So if we implement that in, right, and um, if we think about that score differential, and in highs, basketball is a high scoring setting. In aggregate, the score differential, I guess conditional on wins, the score differential looks pretty normal, right? And that's a not a bad starting place to use as a potential density function where so we represent the score differential as a normal distribution with a mean and a variance. And so what we're going to look to do, and if we do that and we focus on that Bayes factor or the inverse conditional, right, we can actually substitute it in, do the math, and come out with we can decompose the probability into discernible, meaningful factors, right? So if we look at the log odds of the probability of a home team winning, right, we have the prior belief, in the game, and then if when we simplify out the math, we end up with that middle term, which is the ratio of the variances, right? And that's kind of our outcome conditional dispersion at any point in time. And then that last point, that last part is if we look at is our standardized kind of Z score, which we can kind of think of as, the evidence, which, how closely does the outcome match, the evidence, based on historical data. And so we can, given any distribution, you can work to simplify that to try and, discern some type of understanding from the individual components from it. So that's kind of what we tried to do there. And so we haven't touched any data yet. We haven't done any type of regression. And again, I would suggest that if we don't want to use a normal distribution, we could probably just use a mean, right? It might not be as complete, but it might do the trick. Um, so to estimate this, right? We used a few seasons of NBA data. We just pulled the public play-by-play reports and built a game, a season game minute um, data frame that ended in regulation time. And so minute observations course to 48 minutes, so 40-minute games. And our training sample consisted of all games from 2021 to 2022. And our prediction sample that we held out is 2023 season, right? Um, and then, of course, I kind of don't have the numbers here on the slide. Then we divided in the training sample um, into games won by home teams and games won by or lost by home teams and games won by away teams. And if you look, the home advantage in those games is exactly what you would imagine. And if we just plot that data, right? If we just plot the average score differential conditional on wins, and that solid blue line represents the average across throughout the progression of a game. And the red line looks as the average score differential represented in terms of the home team uh, for games that the away team won or the home team lost. And what we see there is a clear, straight, linear, upward sloping line to estimate. Now, right, and that is our real empirical effort. That's our job to estimate. No, that's pretty straightforward to estimate. You couldn't ask for a straighter line to put a regression through there. Um, that sort of dotted blue lines that go there represent the variance of the score differential, and we see that kind of real tight when the game starts and expands out, and it tightens up a little bit as the game progresses to the end, right? And And the same thing with the away team, right? So these two things, the mean and the variance are what we need to estimate uh, in order to complete our win probability model, anyways, our empirical approach, right? To satisfy the normal distribution, I guess. So how do we do that? Right? Well, we just aggregated up the average score differential, right, and the standard deviation of the score differential at every minute of the game across wins and losses, or for home team, the score differential across every minute of the game, across wins and losses, right? And with that, you get 48 observations, right? And then we just fit a real simple OLS regression to estimate the mean score differential at every second of the game and to estimate the standard deviation, right, or the variance at every second of the game. And to do the variance, we just put a simple quadratic function on that to get that uh, curve. And so the plot on the left has you know the average data that was the same on the previous plot, and then the dots are our predicted values, right? Actually, it's probably the way the dots are the actual data, and the line is the fitted values, and the same thing on the right. So we could see that it, when we partition our data and we use the outcome first approach, right? I think that the estimation procedure becomes really quite straightforward to do. Um, and then, right, once we have that, it's just a mathematical exercise to go back and derive those uh, inverse conditional likelihoods for every minute of the game and predict out a sample. So for every minute, you go and we calculate the moments, right? The mean and the standard deviation, apply it to the actual score differential in an unobserved game, compute it in there, and then we have our Bayes factor, right? We've actually boiled that whole problem down to two simple regressions, and then multiplication and I guess exponential multiplication and subtraction. Um, and then all what we really need to do there is come up with um, a reasonable or accurate pre-game belief for our prior odds um, component of it, and then multiply it up. Uh, and I guess so, and so for what we used here was the money line odds for that game at the start of the game to calculate the the game specific priors for every game is we just use the money line. And I guess if you really wanted to, you could use a range of values, or we can even build in some complexity into that. And if the money line isn't good, and you could build a model based on factors or strength of opponents in order to come up with those odds. Although I would suggest that most of those are kind of pretty well incorporated into the money line, right? And so again, if we do that, here's an example of one of the actually in the paper. I write this, and I literally, we literally did it, is just randomly selected 10 games and plotted them. And here I have a couple of them. And so we have one game here between Phoenix and Minnesota, and the pregame win probability by the money line was the home team winning by 60%, and that's represented by the green line. And then we see kind of throughout the game the home team had uh, a lead that lead throughout the game actually, and it just kind of increased as they won the game throughout. And our win probability kind of might move up as you would expect with up and down movements or based on the change, right? And then looking at a different type of game where the home team was an underdog, at about 40%, and the game kind of the score kind of oscillates where the home team was losing at the beginning and the win probability dipped down, and then you see as the home team you know started to win the game, you see that the posterior probabilities or the in-game probabilities actually go above the pre-game probability of zero point 0.4. And then as they score enough into double digit goals, it actually gets above 50%, and then the away team comes and had a lead, and the pre I guess the posterior probabilities or in-game probabilities kind of oscillate nicely, with the score as you might expect, right? So it's not really smoothed out, right? It's kind of really moves with the data. Um, and so, how good does their model perform sort of overall? And I thought about a number of different ways to check calibrate the model and check the robustness, and kind of sticking with the simplicity of the approach in that we really just we took our predicted values at every minute, right? And we just used a simple logit, regressed it on whether or not the home team won. And we estimated our parameter estimates, right? When we came up with the intercept being, negative 0.1, and the slope being 1. So if we interpret that, right, the slope is indistinguishable from 1, which is what you would expect from a model that sort of perfectly fits the data. And the intercept is slightly negative, which would suggest that the model, right, slightly overestimates home win probabilities, right? You would kind of think that would be 0. A 0-1 would be a kind of perfectly fit model. But if we look in kind of real terms, we're looking at 0.1 of a win probability at the extremes, right? So there's probably enough error in the whole model to make that not I don't know, too meaningful. Right? So I guess we tried to recast this in-game win probability model or a problem using just a different approach and using data different than the previous literature does. And in doing so, one of the things that kind of I liked about it as an economist is you can kind of try to you can decompose these win probabilities into parts, and depending on distribution, there's distributions that allow you to get kind of different types of meaning from those components, right? And if at a minimum, you always have that, you can always take apart that pre-game win probability belief and the actual in-game behavior, the evidence. So in terms of limitations, I think one of them is this distribution shift, that choice of distribution, that normal distribution, kind of needs to be consistent. Well, doesn't kind of, it needs to be consistent between your training data and your your prediction data, your live updates in game, right? So if rule changes or some things alter this score state distribution, right, you're going to have to recalibrate your data and wait for sufficient data in order to have meaningful estimates. Um, and I guess, specification dependent, right? Our results clearly depend on our chosen likelihood from the score state, right? So we can choose a different a normal distribution or choose a different distribution, and we might end up with something, um, you know, um, a different win probability, anyways, right? So we could, you know, I, in the presentation or even in the paper, we kind of talk about a richer game state and actually including other things in there. But I really do think that other than maybe let's say football, where you have the ball, that score state in those continuous games like hockey and basketball, that score state conditional on time really includes you know all the information about the likelihood of the team's going to win, conditional on the quality of the teams. And so I don't know if really expanding out that X variable to um, have a whole bunch of other factors kind of takes away a little bit from the approach, because you start to take those factors. um, you definitely don't want those covariates to be part of your pregame probability. Um, and so I think and there's these it supports the model, I guess, supports the approach supports this analytical kind of framework, and which could be, it's lightweight, computational, it could be done on um, you know uh, easily can be computed in game, and across a lot of different, I don't know, platforms, if you will. Um, and I guess you can apply it to, let's say, if you wanted to say win probability added as a metric, or other applied to other types of areas in sports analytics, and maybe coaches decision making, or even I know one of my grad students kind of is looking at using some win probability models to examine biases in coaching decision makings, right? Those type of things. um, so I think it has some applications in there. So um, yeah.
All right.
Thank you.
Thanks very much, Kevin. Great. So let's open the floor for questions. Please just, there's enough of us, so if you just want to unmute and ask your question, that would be great. I'm just going to turn the gallery mode on here. Um, yeah, so maybe I'll start with one while we're waiting for others. So I liked the part of the end. Like, it seemed sort of a very observational approach rather than like something that you could make decisions based on, because there's not like an explicit consideration of covariates, perhaps. Um, I guess like so given that, like, currently, what do you think the application for this, like, this approach should be? And like, so there's media are already, let's say, watching or presenting in-game probabilities. How are they computing them? And is your method something that would be favorable for them to use?
Well, I don't know exactly how the media are computing the in-game win probabilities, right?
Mhm.
For it. Um, there has to be some type of, engine model in the background doing it. Uh, uh, and however, uh, you know, complex that is, given with, how they're updating it on a regular basis, it can't be that computationally intensive, right? It can, and if you look at the academic literature, it it probably, I'm kind of just, it. I have trouble seeing them implementing some of the models, solely based on them in the academic literature, which are computationally intensive, and and yeah, to to be able to get that live, right? So,
Mhm.
um, but I'm not, I actually don't know how some are doing it. I don't know how much of a theoretical kind of underpinning is going to their probability estimates either in order, right? And that really is where you are able to sit back and you could run. I'm an economist, right? You could so that's just the way I think, but you can run evaluations and calibration and examine the data to see if it is. But to be able to be certain of it, being having that framework, but you can you know uh, not to overuse decompose, but back out of where your model comes from, and then you could change it as you need to. If the normal distribution isn't the right distribution, use a different one, right? I know I've done the model for the NHL, and the normal doesn't work quite as well, which makes sense from it, right? So you just kind of back that out, right? So it's really lightweight. You can. Now, I'm not going to say you're going to do it by hand, but you can do it in Excel easily, right? You're literally just calculating Z scores.
Mm.
And those parameters, how many parameters? You had a parameter from the OLS regression for the mean, you had two, and you had three parameters for the standard deviation, right? So, and I've built models like, the rest of the literature and lots of data and all those approaches. Um, but if you gave me, you know, this line to estimate as a academic, there's a nice relationship, right? But you're just not normally when we see those lines, it's aggregated data and it doesn't account for all the factors that you need to, right? That's just average, right? But if you use that prior, you know, I would suggest that's already in there. Now, and sports is a good environment to do that. So, I think they could, I don't know if TV is going to use it, but I think it could be using that type of, environment, or even, if my work with whatever clubs or teams is those, people know the game extremely well, right? And the black box and trust in this method is tough. And having just having the numbers that you can just kind of back out from adding and subtracting makes sense. If I was, it doesn't need to be, I'm not saying you want to use it in real time, but just if you're going to use it as part of a evaluation framework, let's say, for your players or your team, or if I was running a team, I would want to know what my win probability was regardless of the outcome, because at some point you lose some games you should win and win some games you should lose.
Mhm.
Maybe you don't change your strategy anyways.
Okay. Just maybe a uh, different question, maybe not appropriate, but I was kind of just wondering, looking at your plots, like, is there evidence for, or could you quantify momentum uh, based on the outcomes of your models?
So, so that's the thing, right? So here, right, there's no momentum or anything like that, right? It's entirely agnostic of that.
Yeah.
Um, and so I actually, kind of, I don't know, say stumbled this approach or by this approach, not from building a win probability model. It was more from decomposing or, deconstructing, let's say, in-game gaming markets into components to find out, test behavioral factors. Um, so I'm not, and 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 the simplicity of the model is kind of a little bit hard to think that it's accounting for everything other than looking at the win probability. Say, oh, well, it's probably okay. You got those things that go up when they should and down. Because it's natural to want to lag that X and just condition your X on the previous, but then you're taking out your prior. It just doesn't. It's just not the way the theoretical framework flows into the empirical model. So I'm not sure that or I have to think about how building in momentum into the model. But if we took the model, let's say, as fact, no momentum, I'm pretty sure, right, we can, you know, sit down in a half an hour, come up with a test for momentum,
Mm,
right? Look at the data, find a find an environment where it switches
yeah.
or some type of construct that, right? And then say, convince ourselves that the only possible solution for this model to deviate from the truth is momentum. To test for it. I'm not right. And say, I think there's room for that. And that was kind of where in the first slides, I wrote I think these in-game win probabilities have lots of applications to
Mm,
to to different things outside of sports analytics, psychology, behavioral, economics or whatever it is, just testing, I don't know, do markets behave? You can use this as an in-game win probability model versus this probability model. And there's information in there. That's all I'm saying, right? And uh, yeah, so I'm not sure we're going to model in momentum, but I think we can test for it or something
yeah.
else.
That's kind of what I was
Yeah,
wondering. Like you could
yeah.
observe it, like just
You can observe momentum
yeah.
that would deviate from it. Yeah.
Um, looks Oliver, do you have a question?
Um, yeah. Oh, but you can go ahead too, Dave, if you want to follow up.
I just have one more.
Mm.
So this looks like it works really nicely for basketball, which is a high scoring sport. What
Yeah.
about low scoring sports like soccer or even hockey?
Yeah. So, like,
I mean, I guess like the
choose your
plots are,
distribution, right?
yeah. I mean, I guess like the plots would just be less dynamic. Like, would the probabilities change unless there's like they only change when there's goals scored or in this case baskets.
Well, no, not really. No,
Mhm.
because you would have, if you look at your X, right? So if you think about, X is conditional on time.
Right. Okay.
And if you had a 2 goal lead, or think about a 1 goal lead at you score in the first minute, right? And that marginal benefit of a let's just say scoring a second goal, that changes over time, right?
Mm,
Because the other team has more or less time to score, or
right.
there's the mark, and it changes. The data it's in the data, and it's exactly like you would imagine, increasing marginal, you know, increasing, marginal costs at decreasing rates. It's exactly what you would imagine that they as it should. Um, And so I know for hockey, what I have done is instead of using a distribution for X and the normal, what kind of I, I, I don't know, in my paper, and I like the arithmetic of it, and I like I like simplifying the math and decomposing it. I thought it was cool and it worked out.
Mhm.
Um, but for hockey, the averages work out nice, right? Because this the goal, if you just use the mean, it goes up nice, and really, a multinomial logit rather than a distribution on that, and you estimate the likelihood of the score, no, the score state conditional on time and the win. To take all the home wins, estimate the probability of -4 to +4. What's that? Nine states, you know, given time, 60 or whatever it is you want to do. You can do seconds. The benefit of that is kind of low, right? You can just extrapolate in between. And you run that, and you end up with smoothing as soon as you put that regression in compared to this one. But that's another way to go about it, right?
Mm,
I'm sure soccer people, now people know distributions better than I do. Um, but I'm sure there's different ways to examine that X, right? That you don't necessarily have to kind of do the math and throw you can estimate it. We could have estimated, the instead of doing the math and calculating the mean and the variance, if you will, and aggregate up. We could have estimated it with a a Bayesian regression, or then the language becomes confusing though. In terms of using Bayes' rule and then saying I'm going to use a Bayesian regression, because then it shouldn't become confusing, but it is, right? Because well, you're using kind of the same terms, right? But I think there's a lot of things you can do with that X, right? That relationship. It's pretty stationary. It's nice.
Right.
You can use a Markov. You can use Markov in it if you want. You can do anything you want. It's just that, right? And it's simple. You could do a whole Markov chain based on that, and you got two of them, and then divide them. You just come up anywhere you can get a probability, you can do it. Take the mean. Any yeah, and come up with a prior.
Good. Thank you, Oliver.
Yeah, I'm mainly just trying to understand things. Let's see, looking at this slide, you say pushing the posterior. Oh, no, sorry, let me back up a second. I think it's very interesting to take this Bayesian approach to combine the pre-game prior with dynamic updates. Very, very nice. And but looking at this slide, so the posterior is actually the probability of the large lead, right? Let's say the lead is what are we doing? Basketball, a 10-point lead. Then you're saying the probability of a 10-point lead, given the current score differential. No, what is it?
Yeah.
Given what actually is above 0.7? It, yeah,
No. So here, right? So
yeah,
you got it. Let's see. All right.
yeah.
So the posteriors, right? The odds of the home team winning,
Ah, okay, okay,
which just converted to probabilities.
okay, okay. Yeah,
But you're right. This Bayes factor, the likelihood,
okay,
you're always,
yeah,
what's the probability of being up by 10
hmm okay.
at
Yeah,
1 minute, 2 minutes, 3 minutes? You got 48 minutes, right?
yeah,
For a data set, right? And so for that, you do need enough data at some
yeah.
point, because at the beginning of the games, you're not up by 10 very often.
hmm
But that's kind of that's what the regression helps with.
Right.
That
Okay.
idea. Yeah,
Okay, I get it. The posterior on that slide refers to the posterior odds, not the data posterior,
yeah.
but that's okay. So I wanted to ask, and I feel like you addressed this issue quite a few times, and I'm trying to sort out what you said. So on the richness of the state, I guess I have two questions about it. So are you endorsing adding more covariates to the X, or are you saying that would somehow make things more
Well,
complicated?
no, I guess I'm saying, so if you think about a game like, I guess I'm saying that if the information is in the pregame prior, I it's not necessary to put it in your
Uh-huh.
X,
Right.
because it's in the pregame game strength, right? Weight of, I don't know, rest, injury before the game. That's in the prior. That's the things that everyone is hoping to control for. It's on there.
hmm
It just is.
hmm
It's kind of like an easy way out. But in the NFL, what's not in what the score state is a big part of it. But what's not in there's who has the ball, because it's
hmm
different if you're up by 4, who's up by
Yep.
4, but up by 7 with
hmm
the ball with 30 seconds left compared to not with the ball.
hmm
So there, right? Boom,
hmm
that belongs in the code in X.
hmm
You
Okay.
know,
hmm
but if you're in your, I guess you could put power play, not power play in hockey. You know,
hmm
because that's not in there, but kind of almost is in the prior.
hmm Right.
How are you going to even make that argument, right? Like it's natural to want to control things,
hmm
because that's what we spend. I don't know. We spend so much time accounting for factors so
hmm
we can isolate what we want to test for. Except, it, it it's already in there.
Yeah.
Yeah.
Yeah. Yeah, so it should be if you add to X, you should be adding information that's not available before the
Yeah.
game. If it's available before the game, it should be included in the prior. Yeah.
Or if you change a different prior, right? You could
Yeah.
like if you don't want to use the market,
Yeah.
and you want to come up with take the weight of two
Hmm.
take the weight of two teams winning percentage come into the game, and then you think you need to put something in that X to account for something. Yeah, well, Bob's your uncle, right?
And then, sorry, last question to understand. So, but in how you presented it, you just have the score differential time. And then you talked about conditioning on the history, which is another obvious thing that's not available before the game. So you might think it makes a difference, for example, whether, if you have a 1-0 lead, say in hockey, whether you've been leading since the beginning of the match, whether there's been goals back and forth. So I guess I'm a little, so why do you not think that,
Well,
why is it X of T? Why isn't it X of everything, all the X's up to T?
yeah. As someone who did it, I know it doesn't work. But
Hmm.
so you got to think about it. You're continually that X of let's say T minus one. It has it has all of that in there, right? Like if you're just regressing, you can't just wait by your pregame again. You're because in order if you regress, let's say you want to examine X of T, right? So X and a function of time, and then you put in X minus one. That's going to explain everything. Right, the probability of your score state conditional on what it was a minute ago is going to explain everything. So all the time's out the window. Now you're just kind of, you know, finding out, what is the previous score state go. So the question is really, you know, is momentum a thing? Doesn't matter if you're down by one or up by one at the at the end of the first period, right, given the quality of the team in the prior. And I would, looking at the data and you know, I would say it probably doesn't matter. It's good teams are still going to win that game more often than they don't. Right? How you got there, it's kind of we like to think it matters that probabilities happen. Good teams are outplaying them, and they have a poor first period, but they or I should talk about basketball, but and poor first quarter, but they play more often than not. They better two quarters, and that's in the data, right? That you have. So, but all those things about that you know momentum's a good one. Maybe some type of behavioral factor in the game that's not in the model at all, right? And um I would be surprised, Dave asked a question about, let's say, the computing pregame probabilities on it. I'd be surprised if that's in that model too. I have no idea. But that it just seems like it's nice to want to thing on it, grab onto that, but is that really happening 90% out of the 100, or is it not happening 90% out of the 100? I would say it's 99 to the other one, right? And it's more just kind of on the wrong side of a probability, which we like to think of it as, not to be too Kahneman Tversky, we like to think of it as a small sample. But there's evidence of that out there. But no, that's stuff that's not in there for sure. But again, I
Yeah.
think we can use it to test for it.
Right, right, right. Yeah, there's quite a lot of work on whether there's momentum
Yeah,
between games within a season. I haven't seen much on whether there's momentum within a game, and yeah, that's a really interesting question, as you're saying. Yeah, and yeah, cool. And as you say, we could test for it in this model. Yeah, I love it. So, okay, thank you for patiently answering my
no,
questions. So that's
Great. Okay. Well, I think with that, I'll just conclude the questions session and conclude the talk overall. So, yeah, thank you, Dr. Mongeon, for really interesting talk and answering all of our questions. And yeah, thanks again.
I appreciate it. Thanks for having me.
Awesome.